Okay. Sorry, that was a little load today. Before we get going, I wanted to make a couple announcements. So this is just a reminder that we have our Unit 1 exam coming up kind of soon. So it's Friday of next week. So we've got a little more content to get through. We'll have Review Day, Community Day in between, but you should begin studying for that. On that note, if you haven't begun studying already, I should say. On that note, posted a couple things. So one thing that I like to do is post a full-length practice exam so that you can test yourselves basically how effective your studying is. I do want to add the caveat immediately that it's very important that you don't accidentally memorize the practice exam. So I do try to pair the questions topic by topic to what is going to be on the real exam so that you know what topics to emphasize in your studying. But if you're doing word association, the practice exam might actually hurt a little bit because I'm drawing from a topic. And so if there's a question from that topic on the practice exam, there'll be another question on that topic on the real exam, but it's not going to be the identical one. So you really want to make sure that you don't just pick the answer that was right on the practice exam on the real exam. So they're an indicator for you what you should be studying as a big picture, not specifically the answers to those items. So what I recommend doing is using it as kind of like a double check of how effective your overall studying process is to that point. So study the topics as they are in your notes, as they are in our outline/study guide, as they are in the slides in the textbook. Then go ahead and take this at some point to see how far you've gotten. Do you generally understand these topics to the depth that we expect? But don't focus on trying to memorize these questions. If you're going to go through them in detail, what you should be doing is looking at a question, asking yourself, okay, what topic is this testing? What part of the unit was this? What general concept is this? Okay, what do I know about that topic overall? Do I understand why the right answer was correct? Do I understand what those wrong answers would mean? Do I understand why they're wrong? What are other similar ideas or questions that might be asking about that same topic in a different way? So that's how you should be treating that. So basically, if you are going to pay close attention to the practice exam, you have to pay really, really close attention and kind of go through it kind of piece by piece rather than just learning. Okay. So hopefully that will be useful for you. Some students have told me that they are very useful, but I have had some students who accidentally memorized the practice exam and did worse than they would otherwise do. So be careful about it. So that's one thing that is posted. It does contain some content from our upcoming lectures, but I think that by the end of the day, you should have the ability to answer at least most of the questions. So you don't have to click into that right now. You don't have to start using that right now. I just want you to know that it's available when you're ready for it. That's what I want to remind you of. Okay. Yeah, so the exam's upcoming. Practice exam is posted. There is also a tool for looking at electrochemical driving forces that I recommend or suggest you use to kind of test yourself. Do you understand the electrochemical driving force or not? So I'll show you how to use it today in a little bit, but if you're looking for the link for yourself, it's in the Brightspace announcements. It'll ask you when you click on it, do you want to make a copy of this file? Yes, you do. That's because I don't want you to accidentally change the code that's in it and mess it up for everybody. So you're going to be working in your own personal copies. Any questions about these at this point or from the class? In that case, we'll continue where we left off with our electrochemical driving force and our new understanding of the equilibrium potential. Last time, we talked about chemical driving forces, where we have pretty much all molecules reacting to chemical gradients. We talked about the electrical driving force, where we have charged particles specifically, so thinking ions, reacting to the fact that cells have a charge inside them, basically. And there's a charge on the ion, so we're going to have attraction between opposite charges. We're going to have like charges repelling each other. So when we're trying to figure out what an ion is going to do, we're going to need to combine our understanding of the chemical driving force, the electrical driving force, to create this new concept called the electrochemical driving force, which is really just a sum of those two simpler, hopefully, pieces. So if we're trying to figure out what direction the electrochemical driving force points, something that's helpful is something called the equilibrium potential, which is where we left off. So a reminder of how we're looking at these terms, right? Vm indicates to you the membrane potential. So that's telling you what the charge on the cell is at a moment in time. So it has a polarity. So this is telling you the inside of the cell is negative. And it has a magnitude. So this is telling you that the magnitude, how strong this is 94. It's measured in millivolts. So that's our unit on that number. Okay. So that's our membrane potential. Our equilibrium potential is going to exist for a specific ion. So this X here is a placeholder. When we look at an equilibrium potential, we're going to be looking at the equilibrium potential of potassium, the equilibrium potential of sodium, not an equilibrium potential just overall. This is because we're accounting for both the concentration gradient of sodium and the electrical driving force on sodium. Okay? If we're looking at potassium, trying to figure out its equilibrium potential, trying to look at its electrochemical driving force, we'd want to look at the concentration of potassium specifically, not sodium. So we're going to have different numbers for these two things because our concentration gradients that are relevant for a specific particle or molecule are just the concentration of that thing specifically. Okay. So we find an equilibrium potential or define the equilibrium potential by finding the charge on the cell, the membrane potential, where we have equal and opposing chemical driving forces and electrical driving forces. So in this example, it's showing you the setup for how we found the equilibrium for potential for potassium inside a cell, right? So this would be a cell somewhere in your body. Okay? In your body, you have some typical concentration of potassium ions in your blood, in your tissue. You have some concentration of potassium ions in the typical cell. Those create a chemical driving force because the concentration isn't the same. So that CDF is based on values that we would like measure in a person. Okay. So in this case, we have a chemical driving force that is pointing out. So here we see that you have more potassium inside the cell than outside the cell. This is often based on the action of a sodium potassium pump. So this is actually like a true fact about your cells. It's our example, but it's also true. Okay. So if we wanted to figure out what our equilibrium potential would be, so the point at which potassium ions would stop moving, at what point there wouldn't be any net force, no electrochemical driving force on a potassium ion, we'd be looking for the point at which we have an electrical driving force that perfectly fights against that chemical driving force that we know exists because of how bodies are. Okay. So in this case, we're looking for an electrical driving force that would pull potassium into the cell, right? So if we only knew about the chemical driving force, we wouldn't predict that to happen like ever, right? Because that would be against the chemical gradient. But now that we know about the electrical driving force, we know that if the cell is negative on the inside, right, if we have a membrane potential with negative polarity, that's going to pull any positive ions towards that negative charge, going towards the negative charge because the opposite charges attract. Okay. So there's a certain amount of negative that that cell has to get to for that electrical driving force on potassium to be so strong that it equals out the chemical driving force going the opposite direction. So you have movement, movement, movement until that cell gets to a magnitude of 94, so negative 94 membrane potential on the inside. That's how strong we would have to have a membrane potential for this electrical driving force to get big enough the potassium stops. This is how we set up an equilibrium. Questions about this conceptual idea for what the equilibrium potential means? This is the setup. When we ask about electrochemical driving forces and their direction, what we're fundamentally asking about is what direction do the ions have to move to get us to this state, to get us to equilibrium, get us to the equilibrium potential, get these ions to stop moving, at least overall. So usually when we see situations in your body, like when we're talking about neurons in our next unit, you're not going to see a cell that is perfectly at the equilibrium potential for any one ion. Okay. So we're going to see situations where we have a membrane potential. So here we have a membrane potential. So that's the charge inside the cell of negative 70. This is a typical baseline for a cell at rest. Okay. But we know that the equilibrium potential for potassium is at negative 94, right? So we are not yet at the point, negative 94, where our electrical driving force on potassium is so strong that it equals out that chemical driving force, right? We've still got a little ways to go. That membrane potential on there is still kind of too weak to fight against that chemical driving force that is set up by other processes in your body. So in this case, where we have this membrane potential that's a little too weak, right? And we have a slightly wimpy electrical driving force, though it does exist. This means we're going to have an electrochemical driving force heading out. So we can see here that when we have this weak membrane potential, that chemical driving force is still winning out. There's still some extra. We cancel out like a little bit of it, but we still have a little bit of electrochemical driving force pointing out. So we're still overall going to tend to be pushing potassium ions out of the cell if they're allowed to cross the membrane. Here we can see the opposite situation on the other figure. Okay. So here we're looking at a cell that's at negative 100 millivolts. So we'll come to describe this as a cell that's hyperpolarized, so extra polarized, extra negative. You don't need to know that word for now, but we will see things like this happen in the future. All right, so we have a super strong membrane potential here. And in fact, if we compare that super strong membrane potential to our equilibrium potential for potassium, which is negative 94, remember? Right, we now see that this membrane potential is so strong that our electrical driving force beats out the chemical driving force pointing in the opposite direction. And our electrochemical driving force overall points into the cell. So here we can see that by comparing the membrane potential to the equilibrium potential, we can determine whether the chemical driving force or the electrical driving force is stronger at that membrane potential. And therefore, we can determine which direction our electrochemical driving force should be pointing. Okay. Very much. Okay. Cool. All right. So we could build, you see it? Okay. We could build a flow chart for comparing these directions of electrochemical driving forces, these membrane potentials, and these equilibrium potentials. So if we want to determine this, right? So we want to figure out what direction is the electrochemical driving force. We can make ourselves like a little bit of a decision tree. So if this is our goal, we might start by identifying what direction the chemical driving force points, what direction the electrical driving force points. So we're going to identify the CDF and the EDF and their directions. So the chemical driving force, remember to determine that, we're looking at just concentrations of your given molecule, of your given particle, right? So we're looking at the concentration of sodium if we're looking at the ECDF on sodium, or we're looking at the concentration of potassium if we're looking at the electrochemical driving force on potassium. These are going to be specific to that specific particle and that particle alone. Okay. If we have these pointing in the same direction, our life is easy. Okay. So if we have the same direction, then our electrochemical driving force is going to be in that same direction, right? If they both point into the cell, electrochemical driving force is into the cell. If they both point out of the cell, electrochemical driving force is out of the cell. All right. It's when they're in opposite directions that we have to think a little more creatively. And we're looking for opposite directions. And this is where we're going to compare our membrane potential to the equilibrium potential. Trying to figure out, essentially, is the chemical driving force bigger? Is the electrical driving force bigger? And we can do this in part by comparing equilibrium potentials, which are going to be specific to that ion, to the membrane potential, which is the charge on the cell. Okay. So we're going to end up with three possible options. Actually, I'm going to start with our middle option first. Okay. So our middle option is going to be that they're the same size. That's why I'm starting here. Okay. So if we have an equilibrium potential that is the exact same as that membrane potential, then our electrochemical driving force is zero, right? So there's no net movement, there's no overall force if these are at the same point. This means we are at equilibrium already, okay? So no force if you're already at equilibrium. I need to sound out words. Unfortunate. Okay, cool. So they're the same, no force. This means that we're going to have a situation where the equilibrium potential is larger, and we're going to have a situation where the membrane potential is larger. So let's start out with that equilibrium potential. Okay. So in the situation that we have an equilibrium potential that's larger than our membrane potential, okay, This is that situation where we were saying that the membrane potential kind of still too weak to fully combat the chemical driving force. Okay, so in this situation where we have a larger equilibrium potential, this means that our chemical driving force is still stronger. If our chemical driving force is stronger, it wins when we add together, subtract apart our chemical driving force and electrical driving force. So now we're going to have an electrochemical driving force that follows our chemical driving force. Okay. Now, if we can have our equilibrium potential be stronger than the membrane potential, then the opposite could also potentially be true. So to finish this out, our final option, so we have a membrane potential that's extra, extra strong, bigger than our equilibrium potential, which means that it's pulling extra on our ion. So our electrical driving force is bigger than the chemical driving force. In this case, our electrochemical driving force, it always just follows the stronger force. It might get a little bit weak, but it's going to follow the same direction. Okay. In this case, our electrochemical driving force is going to follow the electrical driving force. Okay. So as you're walking through any example about membrane potentials, equilibrium potentials, the electrochemical driving force, this is a way that you can kind of process that information to figure out what direction you're going. This is a sort of step-by-step thing. So for chemical driving force, you're looking at concentration, high to low, the direction of the chemical driving force. For electrical driving force, you're looking at the charge on the ion, you're looking at the charge of the cell. Opposite charges attracting, like charges repelling. And when you're trying to combine them together to look at the electrochemical driving force, we're going to look at the equilibrium potential as the value that the ion kind of wants the cell to get to. We see movement of our ion until we get to a membrane potential that is perfectly equal to that equilibrium potential. Honestly, I find it easier to just mentally move ions in my head until I figure out what direction that happens to be. You don't actually fully have to go through the flow chart if you don't want. But if you want to, if this makes more sense to you to think about it in this way, then you can compare which of these two numbers is larger, which is a little smaller. See that when we have a particularly strong equilibrium potential, that means that we have strong chemical driving force and an electrochemical driving force following it, and the opposite if we have an extra strong membrane potential. Okay, questions about this process? This is something that you're going to want to practice. So as you're practicing, if you have more questions, make sure to come visit me in office hours, ask questions in SI. Very important concept to understand for our first exam. Okay. So we're going to run through one example, possibly a couple examples. So I think we kind of left off here last time, but we're imagining a situation where we have a chloride ion. So chloride ions are negative ions, they're anions. What we're thinking about is a situation where chloride has an equilibrium potential. So that would be E and then subscript Cl. That equilibrium potential is negative 61 millivolts. We're going to compare that to the electrochemical driving force when our membrane potential is at negative 66 millivolts. So what we're trying to solve overall is just what direction are the chloride ions going to go on net, knowing that at negative 61 millivolts, our chemical driving force and our electrical driving force cancel each other out. So take a second to draw this situation for yourself. Try and define the direction of those chemical driving forces, electrical driving forces, and then try and combine them to get this overall force. Make sure you have that setup written down. I'm going to poll you guys in a second. Going. Yeah, I know. Okay, take another couple seconds to put your answers in and we'll go over this process. Make sure you understand what's happening. Okay, let's walk through this in a little bit more detail. Yeah, so we'll just pull up another whiteboard. Okay, there we go. Okay. So in this example, picture, we have a couple extra facts. Okay, so we're going to use those as we think about this and think about why we're actually going to see our electrochemical driving force pointing out. Okay, so for our chemical driving force, hopefully this is the simpler one. So we're looking at chloride ions, high concentration outside the cell, lower concentration inside the cell. So our chemical driving force points in. Our electrical driving force, we do have to keep in mind that we are thinking about an anion. So we're thinking about a negatively charged particle, right? So this behaves a little bit differently than the positive examples we ran through previously, right? So when we have a negative charge on our ion and we have a negative charge inside the cell, this is one of those cases where we have opposite charges repelling each other. Okay? So this is a repelling action. Chloride ions are being pushed away from that negative charge inside the cell. Okay? So our electrochemical driving force, our electrical driving force, do that separately, points out. Okay. So this is our baseline situation, and this is why we have to look at that equilibrium potential to try and figure out what direction overall our chloride ions are going to move. All right. First, I want to imagine this conceptually, and then we'll think about that flow chart so that you have kind of two ways to think about this. Okay. So let's pretend that a chloride ion is just going to be like -1 on that charge of the cell on the millivolts, right? So we're saying that this is a -1 charge moving back and forth across the cell membrane. Okay. So this means that every time we have a chloride ion go in, right? So if chloride ions go in, right? You'd have a negative charge moving into the cell, right? So if we have a negative charge moving into the cell, this membrane potential is going to get more negative, right? So if you have a negative charge move in, if it's a full negative charge, we'd get to -67 when one moves in. If we have two move in, we're getting to -68, and so on and so on and so on, right? That's what would happen if on net, you have chloride ions moving into the cell. So if you notice, our chloride ions want this cell to be at -61, right? So we're moving in the opposite direction of chloride's desired state, right? We're getting farther and farther away from its equilibrium potential, right? So that's how we know this is not the answer. Chloride ions don't want to go into the cell, right? Because we're getting farther and farther away from our equilibrium state if we do that. So instead, right, we're going to imagine our chloride ions. What happens when we have a charge, a negative charge, removed from the cell, right? So we're still imagining a chloride ion as just one little negative charge, right? So if we export a chloride ion out of the cell, right? Now the inside's not so negative anymore, right? So if we move one, now instead of at -66, we're at -65, right? If we move another one, now we're at -64. Okay. We're getting closer and closer to that equilibrium potential, right? So conceptually, that's why we know that that has to be the direction of the electrochemical driving force, right? Because we know once we get to our equilibrium potential, movement is going to stop, right? So we're not at equilibrium now. We're going to have movement in the direction that brings us towards equilibrium, okay? And that direction that's going to get us there is an electrochemical driving force that goes out. means that that electrical driving force is stronger than the chemical driving force. So that pushing the chloride ions away from the inside of the cell, that repelling action, stronger than a chemical driving force. Okay. So if we were looking at that flow chart at our questions, right, we'd notice that our chemical driving force and our electrical driving force in that first setup, they're in opposite directions. So we've got a problem. We actually have to solve for the electrochemical driving force. So we compare the sizes of our equilibrium potential for the ion versus our membrane potential for the cell, right? And in this case, we can see that that membrane potential has greater magnitude. So it's stronger. When we're talking about stronger, we mean greater magnitude, right? The size. Okay, so that greater magnitude, that stronger force. And maybe this is where people got tripped up. Like if we're just comparing on a number line versus if we're comparing magnitude, strength, that gives you a different answer. So we're looking at the magnitude. So when we see that magnitude greater than our equilibrium potential magnitude, so it's stronger, this means that we are following that electrical driving force direction. Okay. And this kind of confusion between magnitude and like a number line is why I really prefer to do this little thought experiment and just imagine which direction of movement gets us to that equilibrium potential. Because that way I don't have to think about specifically magnitude and sign and all that stuff if that part is what was confusing you here. But this is how we set up this problem, and this is how we solve it and double check it. Okay. So right now, actually going to pull us out to that link in the Brightspace announcements. So I would set up here a link for myself. So you can find the announcements here. So you're going to get this electrochemical driving force calculator coming up. Okay. So the way you can use this, you can just make up numbers for yourself, make up any membrane potential you want. So membrane potential is that Vm for the cell. You can make up any equilibrium potential you want for now. There are real ones in your body, but when we're trying to understand the concept, any number will do. Okay. And what you will have to know is the charge on the ion, right? So we're going to need to know if it's a sodium ion positive, chloride ion negative, and so on. Okay. So in the situation that we just looked at, what were our values? Remember, okay? So we would put in for our membrane potential a negative 66. You put in your equilibrium potential of chloride, which we are given a value of negative 61. Oops. Okay. And then final thing you're going to put in, you're going to tell me this is a negative ion we're looking at. That's an anion. Okay. So this calculator that I wrote for you tells you that this means our electrochemical driving force direction is going to be out of the cell. Okay. So when you're using this to generate examples for yourself and double check yourselves, just change the green boxes. Don't change this white box. The reason you're not going to change the white box is this is all the math that's in there to give you that in or out direction. So I wrote this and double checked it for you, so it will give you the right answer. But if you type into this box, that math is going to disappear. Okay. So this is how you can use that for any example you want so that you can generate endless electrochemical driving force examples for yourselves. Do it over and over until you can accurately predict that in or out direction for yourselves. Do this. We'll do some other examples over the next couple of days because I know this tends to be what trips people up. But for now, we're going to move a little bit into our next concept in membrane transport. So membrane transport part 2 is our next on the docket. In this next topic, what we're trying to figure out is how fast are substances going to be transported across membranes? So how fast are they going to move? How can we make them move faster? How can we make them move slower? And we're going to be making sure that we can identify what molecules are able to move across the membrane. How do they get there? We're going to be remembering our concepts of active and passive transport. The active and passive transport, we're thinking of as like the good, easy direction and the hard direction that's going to take energy. And we now know that if we were talking about an ion, we're going to have to be thinking about the overall force on an ion as described by that electrochemical driving force, right? So in your previous courses, you're probably just looking at a chemical driving force, not this bigger picture. Now we know that it's actually a little more complicated if we're looking at an ion. And we also have to add in this electrical component. Okay. But once you've determined the direction of an electrochemical driving force, active and passive are going to work exactly the same as when you saw them in your prerequisite courses. Okay. So when we're talking about transport, we're talking about the movement of something across our membrane. Okay. That's all that transport is fundamentally. Now, it is conceptually true, potentially important to think about, that when we say something's moving, there's always some of an ion inside of the cell, some of an ion outside of the cell, and they're all kind of jiggling around, right? So it's often the case that movement is happening in two directions at once for a while. So when we say transport, we're going to be thinking about the net direction, so like the overall movement of the molecules, and that's our focus. Okay. So just be aware that when we're talking about transport, this is one of those times when we're going to think about that word net. Okay. So we're trying to reach equilibrium, and at equilibrium on net, so in total, our molecules aren't going to move, right? So you might have the case that you have equal movement one direction and the other direction. Potentially, you could have no movement at all. But in this situation, we still have no net movement. We will have net flux. So flux, we're thinking like change, movement, flow, right? Flow is probably the way to remember it, right? So when we have movement in one direction, that's greater than movement in the other direction, that's when we do have net flux. So we overall have net movement in a specific direction. If we're at equilibrium, that net flux is zero, there's no net movement. We're at equilibrium, we're ideally distributed in our nice low energy state. Okay, well, I already told you the answer, so I'll tell you the answer. Okay, so when I said we're comparing this to electrochemical driving forces, this means that we're just using the direction of that force to determine what has to be active versus passive. So if we have a situation where our electrochemical driving force for something points into the cell, if we see our particle going into the cell, so extracellular fluid is the outside, intracellular fluid is the inside. So if we were to observe this going into the cell, it's going the direction it wants to go. So that would be a passive process. Okay, so that's going towards equilibrium in the direction it wants to go. Only when we have to fight against an electrochemical driving force or fight against a force overall that we're going to need to see active transport. So when we pick up next time, we'll be talking about the characteristics of passive transport, spontaneous, no energy, downhill, high to low if we're thinking chemical gradients, and we'll get into some of the specific types.